Symbolically, in mathematical language, we say the optimization we have is to minimize the summation of the p's, let's say from the first to the nth user, they're all together n transceiver pairs, subject to the condition that the SIRs for each user, which is a function of the entire power vector p because of interference, must be greater than or equal to the target constant gamma I. And this holds true for the first, second, up to the n transceiver pairs. And the variable is clearly the p's vector. Now, this is our first optimization problem. We'll encounter at least 5 or 6 more throughout this course. Of course, this is actually a shorthand notation. Okay? If we write out the definition of SIR, okay, then what we have is Pi Gii over summation across all j's not equal to I, Pj Gij plus Ni. And we want that to be greater than or equal to gamma I. If you look at this, say, gee, this is a pretty complicated expression, right? I got a numerator, I got a denominator, and sums in the denominator. But actually, it is an easy problem in disguise. What you can do is to put the denominator to the right-hand side, multiply by gamma, and then move the entire expression back to the left-hand side, subtracting it off. Then what you have is the following. Pi Gii minus gamma times summation of j not equal to I, Pj Gij plus Ni, greater than or equal to 0 for all the i's. What kind of function is this in our variable? Remember, g and n and gamma are constants. The only variable is p. Well, this is just some number multiply pi. This is just some number multiply pj, and this doesn't even depend on the p's. So this is actually an affine function, or we may say it's a linear function. So we are talking about minimizing a linear function, p1 plus p2 pn, subject to the constraint, which is also linear function in our variable p. When we minimize a linear function subject to linear constraints, we call that a linear programming problem. Now, this programming has nothing to do with computer programming codes. Okay? It refers to a mathematical program. So linear programming, this terminology that dates back to 1940s, refers to minimizing linear functions subject to linear constraints in your variable. Of course, if gamma is also a variable, then this is not a linear function in both gamma and p. But that's not our worry today. Our problem today is fix gamma, just vary the p's. And this is an LP. Now, LPs are easy to solve in theory and in practice. But as we will see in lecture 4, when we talk about Netflix price and recommender system, we'll see that the watershed between easy and hard optimization problem is actually not linearity, but so-called convexity. We'll come to that in later lecture. All right, so now we have defined what the optimization problem is, and we have recognized that it is a linear programming problem. How can we solve it? In fact, if you only need to solve this in a centralized computer, then there are many ways to solve this computationally efficient way. But if you want to solve it in the context of a cellular network with distributed action and no explicit message passing between the base station and the mobile station, then that's not easy. In the advanced material part of the lecture, or in section 1.4, advanced material section of chapter 1 in the textbook, we will see the proof of convergence of the DPC algorithm to an optimizer of this problem. In other words, the DPC algorithm is actually a distributed solution method to solve this specific linear programming problem in the physical context of wireless cellular network. Now, before we leave this module of the lecture video and move into the game theoretic interpretation, let's just quickly go through a general terminology for optimization problems. Now, we have seen that optimization problems have constraints. And we say that a variable picking certain numerical value gives you a feasible solution if it satisfies all the constraints at the same time. And if this problem has no feasible solution, then we say the optimization problem itself is infeasible. Now, second, there might be infinite number of feasible solutions, which is typically the case in the optimization problems for this course. And then we're going to pick out the best one according to some minimization or maximization criteria in the objective function. Now, if a particular solution, let's say a vector x with a star on top to denote that it is optimal, we call this vector an optimal solution if it is A, feasible, because otherwise it doesn't even satisfy all the constraints, and B, it is better, or more strictly speaking, no worse than any other feasible solutions. Okay. Now, what do you mean by no worse than? Depends on whether you're talking about minimization or maximization. For a minimization problem, it means that it is at least as small as any other feasible solution will give you in the objective function. So if you pick any other feasible x star, stick into the objective function, which is denoted as f in general, then f evaluated at this x star vector will be less than or equal to that. That's if you are minimizing an objective function. Of course, if you are trying to maximize a function, then bigger the better. Then we say x star evaluated at x star for this objective function will give you an value for the problem that is at least as big as any feasible x vector. This then we call optimal solution. As you can see, sometimes there's no optimal solution. Sometimes there's one, and sometimes there are many, in fact, infinite number of optimal solutions. Later, we'll also try to make a differentiation between globally optimal versus locally optimal. The definition we just talked about, comparison with any other feasible solutions, that is global optimality. If you say that this is no worse than any other feasible solution in a small neighborhood around this point, then we call that solution locally optimal solution. So these are the terminologies about feasible solution, globally optimal or locally optimal solution that we will be using again and again in the future lectures.